Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to continue our study of trigonometry, but we're going to apply trig to non-right triangles. So up until this point, we've basically only looked at how to use sine, cosine, and tangent for right triangles. Now we're going to look and see how trig can be applied to other types of triangles, even ones that do not have a right angle. We're going to skip the do now. That's a little bit of review of angles of elevation and depression, and we are going to look at this introduction problem. So it says, given the triangle below, is it possible to find the measurement of angle B? And I do give you a hint, because this problem does look a little different than the ones we've currently worked with, right? There is no right angle here. And I think we may have done one problem that didn't have a right angle in it, but basically we've only done trigonometry with right triangles. So the hint is, can we turn this into a right triangle? Well, we could draw an altitude to form two right triangles and then use right triangle trigonometry to find different side lengths. So let me show you what I mean by that altitude, and then I'll let you practice before we go over this. But if we draw that altitude right there, now all of a sudden we do have a couple of right triangles that we should be able to apply sine, cosine, and tangent to. So our end goal is to find the measurement of angle B. Pause the video, see if you can get there. Okay, so this is going to be a two-step problem. If I just take a look at this green triangle, right, there's not enough to find angle B, right, because I only know one side, and I need at least two pieces of information if I'm going to set up a trig equation. So I'm first going to have to look at the other triangle. We'll do that one in pink. And I'm going to figure out what this side is right here. We'll just call that x. So my reference angle is 35. Right? That means this side is opposite. This side is the hypotenuse. So I'm going to be using sine. So sine of 35 degrees is equal to x over 15. If I multiply both sides by 15, I get 15 times the sine of 35 is equal to x. We'll round to 3 decimal places here because we're in the middle of a problem. So 15 times the sine of 35, that's going to give us approximately 8.604. Now, I can try to figure out what angle B is, right? Because I now have two pieces of information for this green triangle. So let me just put that in here, 8.604. If I'm talking about B, well, my 11 is my hypotenuse. My 8.604 is my opposite side. So again, I'm going to be using the sine function. So I'm going to have sine of B is equal to 8.604 all over 11. I'm going to apply the inverse sine function to both sides. So that leaves me with B is equal to inverse sine of 8.604 over 11. And then if I punch that into a calculator, and we're going to round to the nearest tenth, that gives me approximately 51.5 degrees. So again, a little bit of a way around not having a right triangle here. We could create a right triangle and then use some of the regular trig that we've been working with. However, today we're going to find an alternate method, and we're going to see that this alternate method we could just use a single equation. However, there may be times where you could, if you forget the methods we've learned today, you could always rely on this method, or at least sometimes you could. So you could always attempt to create right triangles, and then, maybe you can use trig to kind of fill in some different side lengths or angle measurements to find what you want. But today we are going to learn some new trig that will provide us with a shortcut. Two laws today. First one we're going to look at is the law of sines. And again, this is nice to use when we do not have a right triangle. And all the law of sines is that it is a set of ratios. So if I label a triangle with angles A, B, and C, and sides A, B, and C, and notice that they're using A in lowercase a because those are the ones across from each other. All right, so it doesn't matter what letters you use as long as you realize that this angle and this side, those are opposites. Okay, so those are, the angle is going to be opposite that side and vice versa. Turns out that these ratios will always hold true. Now, there is a caveat we're going to talk about in a later lesson, but for now, you can just assume that these ratios will always be true. So, again, this gets us, this gives us a shortcut to not having to create that right triangle that we did for our introduction problem. So let's see if we can apply this law to problem number 1 below. Problem number 1 says we need to find the length of DF. So I need to find the length of this pink side. We'll call that X. Well, let's think about, can we set up two ratios that are equal to one another? Well, I know that this angle and this side are across from one another. So sine of 105 over 18, that's one ratio. That must be equal to sine of 32 over x, because those sides and angles are across from each other. I don't need to have that third ratio in there, right? If I needed to find another side or another angle, I could, but I only need two ratios to create this equation. So the law of sines, there are three ratios that are equal to each other, but you can use any of the two of them that you want to create your equation. Once I have this, it's a pretty easy cross multiplication problem, right? And you can either decide to simplify now or you can simplify at the end. I'm going to be simplifying at the end of the problem just to make my answer a bit more exact. So right here I get x times sine of 105 is equal to 18 times sine of 32. And I will divide both sides by sine of 105. And we'll punch all of that into a calculator. And that means x is approximately equal to 9.88 as we are rounding to the nearest hundredth per the directions. So quite easy, right? Didn't have to draw any altitudes, just were able to set up one equation with two ratios to easily find the length of our missing side. We're going to hold off on doing 2 and 3. Again, they're pretty straightforward. Sometimes they're asking you to solve for a side. Sometimes they're asking you to solve for an angle in which you would need to use inverse trig. But I think the law of sines is a bit more straightforward than the next law we're going to look at. And that law being the law of cosines. So let's go to the next page. You'll notice that the law of cosines has 3 different possible equations we can use. And we can kind of choose which equation we want depending on what we're given and what we need to solve for and which would be the easiest for us to use essentially. So again, triangles set up the same way. So your C's, your lowercase c's, your uppercase c's, those are the angle and the side that are across from each other. Same with A and B and B. You will notice that these law of cosines look pretty similar to the Pythagorean theorem, and they do have a relationship with the Pythagorean theorem. We're not going to get too much into it today. The Pythagorean theorem is essentially, a specific type of the law of cosines. yeah, we're not going to get too much into it today, but there is a relationship there. Maybe we can talk a little bit more about it in class. That being said, again, we're going to look at what we're given in our triangle and use that to decide which of these three equations is best to use. So let's just take a look at number 4. In number 4, we're trying to find the length of BC. So we are trying to find x right here. So let's think about what would be the most efficient equation to use. Well, let's take a look at these equations and kind of look at the different parts. You'll notice that this angle that we're using is always the angle across from the side on the left-hand side of the equation, so the side by itself. And then you'll notice, so that's the same right here, B and B, C and C. And then we have the two sides that are on the side together, so like B and C in the first one. Then we're using those sides again in the cosine portion of the equation. So you'll notice some patterns throughout all three of these equations. On a test, you will have access to the law of sines and the law of cosines. You know, whether you're taking the test at home or whether you're taking the test in class, you will have access to them. So you won't have to memorize them, but you will have to know how to implement them, how to utilize them most efficiently. So again, number 4, we're trying to find the length of BC. So BC is going to be one of our variables. X is going to be one of our variables. And maybe it might be easier if we just call this a little a, because it's across from angle A. Maybe that'll help us set up our equation. So I would prefer to only have one, unknown in my equation, right? I prefer to just have one. So let's just think about if I set it up, let's say I set it up using the second equation here. Let's think about, could I do that? Well, B, this would be B, this would be C. So B squared would be 9 squared. Then I'd have A squared, which I don't know, plus C squared, so 14 squared, minus 2 times A times C, so 2 times A times 14, times cosine of big B. Well, I run into a problem there, right? Because I don't know cosine of I don't know B, which means I don't know cosine of big B. So right here, I already have two variables, so that equation is not going to work, right? So the second one doesn't work. Let's check out the third one. So C, little c is 14, so 14 squared is equal to a squared plus little b squared, so 9 squared, minus 2 times a times little b, which is 9, times cosine of big C. Well, again, I don't know cosine of big C because I don't know C. So here I still have two variables. So it means I can't solve this equation. And again, there's a reason I chose to work through 2 and 3. I wanted to show you that those two wouldn't work in this scenario. But the first equation, let's see what I get when I set that one up. A squared, so a squared is equal to b squared, which is 9 squared plus c squared, so 14 squared, minus 2, just for reference we're using this first equation, minus 2 times little b, which is 9, times little c, which is 14, times cosine of a. Well, I do know what a is. I know that's 62 degrees. So right there, I have an equation with just one unknown, little a. And I should be able to solve this. This is pretty easy because our variable is already by itself. So I'm just going to punch in everything on the right-hand side of that equation. 20 seconds to punch this in. And we end up getting a squared is approximately equal to 120 58.693. And I could take the square root of both sides. And that's going to give me A is approximately equal to, this comes out to 12.60 actually, because we're rounding to the nearest hundredth. So it's 12.6, but we need to have that placeholder. So 12.60. All right, so that finishes up number 4 for us. I do want to do one more example where we're solving for an angle because the algebra does get a bit more tricky, and students tend to make their mistakes when they're solving for an angle rather than when they're solving for a side, like what we just did. So let's look at number 5. You'll notice that the angles are not labeled A, B, and C. So you'll have to do a bit of pattern matching with our equations up here. These three, to figure out where the sides and where the angles should go. So pause the video, take a couple minutes, see if you can choose a correct equation, set it up correctly, and then figure out what that measurement of angle R is. Okay, so there's only one spot for an angle, and it's inside of the cosine function. And I have to use angle R, right, because that's the angle I want to find. So if I'm going to put R right here, right, that means that this side has to be the side across from R. So I only have one choice, right? What's on the left-hand side of my equation has to be, and I'm going to do it up here, it has to be 9 squared, because that is the side across from R. So I get 9 squared is equal to 4 squared plus 7 squared. Doesn't matter the order of those, obviously, because you're just adding those together. So 4 squared plus 7 squared minus 2 times 4 times 7 times cosine of R. So that would be our equation. It's the only one you can use, again, because the angle here, what's inside of the cosine, must be opposite the side on the other side of the equation. So those have to be opposites. Now we just have to go ahead and solve. And if you haven't tried to solve yet, again, I'd encourage you to pause the video and go ahead and do that, just to make sure you can handle the algebra. I get 81 is equal to 16 plus 49 minus 2 times 4 is 8 times 7 is 56, so minus 56 cosine of R. Now I should add 16 and 49 together. It's going to give me 65 minus 56 times cosine of R. I'm going to subtract 65 from both sides. So that's going to give me 16 is equal to negative 56 cosine of R. Divide both sides by negative 56, so I get 16 divided by negative 56 is equal to cosine of R. And then I'm going to use inverse trig, right? So I'm going to have the inverse cosine of negative 16, of negative 16 over 56 is equal to R. And I'm going to round to the nearest hundredth here. So now it's a calculator problem. And that gives me approximately 106.60 degrees. So that would be the approximate measurement of angle R. So again, just a couple more steps when you're solving for an angle. You got to get your variable by itself by using some inverse trig. That is going to do it for this lesson. Again, key takeaways: the law of sines and the law of cosines can be applied when we are dealing with triangles that do not have a right angle, right? So we can only use regular sine, cosine, and tangent for right triangles. Now, though, we have some tools in our toolbox to apply to non-right triangles. So feel free to get the practice in now if you want, but we will have time to finish the rest of the problems in class. Other than that, enjoy the rest of your day, and we will look forward to seeing you next time.